One of the first problems I ran into while building Noet had nothing to do with volcanoes, or atmospheres, or even the planet itself. It was time. That probably sounds strange. However, when we read a fantasy novel and someone says they're 24 years old, we instinctively know what that means. We understand childhood, adolescence, adulthood. But Noet doesn't orbit its star once every 365 days like Earth. It orbits a red dwarf much faster. If I simply measured age using Noet's orbital period, a character who is biologically 24 Earth years old would technically be over 400 Noetan years old. That created a storytelling problem. From the beginning, I knew I wasn't trying to recreate the traditional European fantasy races. Noet wasn't meant to be another world of immortal elves and dwarves. I wanted to create something that felt distinctively different. If my main character was introduced as being 400 years old, readers would immediately bring all of those expectations with them. They wouldn't picture a young adult. They'd picture an immortal elf. The science was correct. The storytelling wasn't. That forced me to ask a much deeper question. How would people on another world actually measure time? On Earth, we accidentally use the same unit for two completely different things. A year is both an astronomical measurement and a biological one. It tells us how many times Earth has circled the sun, but it also tells us how old we are. Those two ideas happen to line up because Earth's orbit takes about the same amount of time as one cycle of human development. On Noet, those ideas separate. The planet may complete many orbits while a child grows only a little, so I stopped thinking of age in terms of orbital years. Instead, Noet uses cycles to describe biological development. Parents count cycles. Doctors count cycles. Teachers count cycles. When someone says a child is 10 cycles old, everyone understands he's about the age of a 10-year-old child. The planet's orbit around the red dwarf is still important. Astronomers study it, historians record it, climate follows it. But ordinary people don't think of themselves in orbital years any more than we think of ourselves as being 8,000 days old. Once I solved the calendar, another question appeared. What kind of planetary system could actually produce it? That question led me to Noet's sister planet, a nearby gas giant. Not a world to live on, but a companion whose gravity quietly shapes almost everything that happens on Noet. Before we talk about calendars and tides, here's a quick recap of why Noet has a sister gas giant in the first place. Its gravity gently flexes Noet's interior, creating just enough tidal heating to keep the mantle active without turning the planet into a volcanic nightmare like Jupiter's moon Io. Those volcanoes don't just shape the landscape. They continually replenish the atmosphere and recycle minerals, becoming part of the planet's long-term life support system. The gas giant also acts as a massive magnetic shield. During powerful flares from the red dwarf, its enormous magnetosphere absorbs much of the incoming plasma while strengthening Noet's own magnetic field. Instead of facing the full force of the star alone, Noet gains an extra layer of protection. Finding the right distance between the two worlds is critical. Too close, and the planet would overheat. Too far, and the tidal heating would disappear. The sweet spot allows steady volcanism without creating a runaway greenhouse effect. Those volcanoes even help regulate the climate. Sulfur dioxide released into the atmosphere forms relatively reflective clouds that bounce much of the red dwarf's infrared radiation back into space. In other words, the volcanoes don't overheat the planet, they help cool it. Finally, because Noet is tidally locked, its thick atmosphere acts like a global conveyor belt, carrying heat, moisture, and volcanic gases from the permanent day side to the permanent night side. Together, these systems keep the planet remarkably stable. With that foundation in place, we can finally answer another question. If the atmosphere moves water everywhere, why aren't there giant oceans? That answer surprised me. Oceans actually became a problem. On Earth, vast oceans absorb enormous amounts of heat. On Noet, that much water would transport far too much heat from the day side toward the night side. It would erase many of the environmental gradients that make the world interesting. Instead, most of Noet's water is divided into thousands of inland seas, Great Lakes, river systems, wetlands, and underground aquifers. Each basin develops its own climate, its own ecosystem, its own weather. Rather than one global ocean, Noet became a world of connected watersheds. The gas giant influences those waters as well. Every few days, its gravity raises gentle tides across every lake and inland sea. Not enormous tidal waves. Breathing, the water slowly rises, then falls again. Some lakes expand by miles. Others expose fertile shorelines before filling again. Entire ecosystems synchronize themselves with these orbital rhythms. The calendar isn't simply based on the star. It's written into the movement of the water itself. That eventually led me to rethink how time works on Noet. Earth gives us one obvious rhythm, day and night. Noet doesn't have that. The sun never rises, it never sets. Instead, people learn to measure time through repeating patterns in their environment. The gas giant provides many of those rhythms. Its changing position, its phases, and its eclipses become universal astronomical markers. But each civilization experiences those rhythms differently. Around the inland seas, its gravity raises gentle tides that shape fishing, agriculture, and travel. In the deserts, where water is scarce, time is remembered through the great storm cycles. As warm air from the day side collides with the cold of the twilight regions, immense dust and ash storms sweep across the landscape with remarkable regularity. Entire generations remember history by the storms they survived. Other cultures follow migrations, flowering seasons, or volcanic cycles. Everyone looks at the same sky, but each civilization learns to tell time through the rhythms of the land beneath their feet. Time on Noet isn't measured by sunrise, it's measured by the living systems of the planet. This also determined where Noet could exist around its star. If it orbited too closely, the year would be shorter than 10 days. The planet would endure constant stellar violence. Rapid rotation would create intense Coriolis forces, disrupting the atmospheric conveyor belt that carries heat from the day side to the night side. The atmosphere itself could eventually be stripped away. If it orbited too far away, beyond roughly 30 days, the already dim red dwarf star wouldn't provide enough energy to sustain liquid water across much of the planet. Noet sits in the narrow middle, roughly 10 to 30 days from its star, close enough to remain warm, far enough to survive, slow enough for the atmosphere to move heat around the globe efficiently. It's an incredibly narrow, habitable window. Perhaps my favorite consequence of all this is the night sky. The night side isn't simply dark. Sometimes the gas giant becomes a massive crimson lantern, hundreds of times brighter than Earth's full moon. Sometimes it disappears completely. Sometimes it eclipses the star, surrounded by a glowing red halo. And whenever the red dwarf erupts, enormous auras ignite across the sky. Not green like Earth's, deep violet, electric blue, magenta. Curtains of light dancing across volcanic clouds while rivers of lava glow below. The planet never truly sleeps. It simply changes its heartbeat. When I stepped back from all of this, I realized something unexpected. I hadn't really designed a planet anymore. I designed a planetary ecosystem. The star, the gas giant, the atmosphere, the volcanoes, the lakes, the tides, and even the calendar all depend on one another. Noet doesn't survive because one system is perfect. It survives because every system continually compensates for the others, and that, more than anything, became the defining idea behind the world I was trying to build. As I kept building Noet, I realized something surprising. Designing the planet was only half the challenge. The real question became, how do people actually survive here? What does it look like to build a civilization in a landscape carved from stone, shaped by storms, and constantly responding to a living planet? In the next episode, we'll finally leave orbit and step onto the surface. We'll explore a Calrix Hoodoo desert, how its towering rock formations were created, how cities are carved directly into the landscape, how an entire civilization moves, stores, and recycles water in one of the harshest environments imaginable, and why Noet's infrastructure isn't something built on the planet, it's something built with the planet. I'll see you in the next episode, and in the meantime, may God bless and keep you.